Hey everyone, welcome back to physics. This will be lecture 19 of the course. And in this section, we're going to take a look at some examples that involve the use of Newton's second law. So similar to the last lecture, but the focus here will be on Newton's second law. So let's go ahead and jump into it. We'll call this section 4.2, using Newton's second law, the dynamics of particles. So in this section, we're going to look specifically at problems that make use of Newton's second law. Let's remember what that law said, Newton's second law. So the sum of the forces exerted on an object are equal to the object's mass times the acceleration of the object. And this will be the central idea that we'll make use of in the coming handful of examples. Now, specifically, this law this section we're going to be dealing with bodies that are not in equilibrium, so bodies that are experiencing some kind of acceleration. Okay, so let's go ahead and get started. Our first example, I'll write it out here. Our first example says an ice boat is at rest. So a boat that's got skis on, it's an ice boat. An ice boat is at rest on a frictionless surface. Okay. A steady wind is blowing such that uh, 4 seconds after the boat is released, so steady wind is blowing such that 4 seconds after the boat is released, it attains a velocity of 6 meters per second. Okay. All right. So picture what's going on here. You've got some kind of a boat on ice. So it's almost more like a sled. But I think the idea here is that you've got like some kind of it's like a sailboat sort of thing. Right? And you've got the wind kind of pushing it. Okay. And the wind pushes it, and initially it's at rest, but then 4 seconds later, the boat is traveling at 6 meters per second. So it starts out at rest, 0 meters per second, and its final velocity 4 seconds later is 6 meters per second. Okay, so the question is, what constant horizontal force does the wind exert? Okay, what constant force does the wind exert? And let's just assume the mass of the boat is 200 kilograms. Okay, so there's our problem. Okay, so over this interval, 4 seconds elapses. Okay, so the boat goes from basically 0 meters per second to 6 meters per second in 4 seconds on a frictionless surface, and this acceleration is due entirely to the force exerted by the wind. So let's look at a free body diagram here. Simple problem, right? You've got the weight of the thing. You've got the normal force at work here, of course, since it's suspended on the surface here. And then you've got the wind pushing it. Right? There's nothing else. There's no friction involved. There's no other other additional forces being exerted on the body. Right, so the y coordinates here are in equilibrium, right? So they're not really needed. The normal force and the weight of the boat are sort of in equilibrium. So really what we'll be thinking more about is, and what we're trying to figure out is, what is this guy here? What is this force due to the wind? Well, we're told what the boat's acceleration looks. Well, we're told what the boat's velocity and initial and final velocity is, and the time it took to increase from 0 to 6 meters per second. So we can calculate the x component of acceleration. Right, so it's going to be equal to that VF minus V initial, and I'm putting the x component just because we're talking about just the x component of acceleration, and then delta t here, right? So we end at 6 meters per second. We began at 0 meters per second, and it took us 4 seconds. And so that means our acceleration is 6 over 4, which is 1.5 meters per second squared. Okay, so we know the acceleration of the boat, we know the mass of the boat, and so using Newton's second law, we can identify the net force, right? So using Newton's second law, we can find Fw. Okay, so the sum of the forces are equal to the mass of the thing times the acceleration. Okay, so that means, again, the sum of the forces in the x direction is really what we're talking about here. So the sum of the forces in the x direction is just F of W, the wind force. That's equal to the mass times the acceleration. Okay, and we can kind of plug all this in, and so we say that the magnitude of the force of the wind is equal to 200 kilograms, the mass of the boat, times its acceleration, 1.5 meters per second squared. And we see that that is equal to 300 newtons. So in order for this boat on this frictionless surface to achieve this velocity in this time, a force of 300 newtons, a constant force of 300 newtons has to be applied. Okay. All right. So in this example, we didn't assume any friction force. What if we add friction to the problem? So for the next example, let's kind of piggyback off of this. Let's add friction to the previous problem. Okay, let's say the acceleration is still 1.5 meters per second squared. So we'll let the acceleration equal 1.5 meters per second squared. But now let's say there's a friction force of 100 newtons. So let's assume there is a friction force of 100. Sorry about that, 100 newtons. Okay. So the question would be then, what must that constant force of the wind be now? Right, so given that there's friction involved, but the same acceleration is required, what force, the force obviously has to increase, but how much? So let's look at a free body diagram here. W equals mg, the normal force. You've got a force of the wind, and then you've also got some kind of a kinetic friction force, which I'll just denote F sub. We'll just put a little f there, that's fine. So you've got some sort of friction force. Now the thing's accelerating, so you can see I kind of drew the arrow a little smaller. If you know these things are happening, if you know that this force is going to outweigh this force, then it's okay to make the arrows a little smaller. All right, just it's all part of the diagram. Make it as good as you can, given the information that you have. But given this is, we really again don't need to worry too much about the y components. They're they're in equilibrium. The thing's not accelerating in the y direction. The x components are what are interesting here. So the sum of the forces in the x direction will equal the mass of the object times the acceleration in the x direction. And what are those forces? Well, you've got the force of the wind, in that direction towards the right, and then opposite that, so let's put a minus sign, you've got the force of friction. And those two are equal to the mass times the acceleration in the x direction. Okay, so what we're interested in is Fw, so F of W is equal to the mass times the acceleration plus whatever this friction force happens to be, right? Okay, and we know what all of these things are, right? So we know we've got 200 kilograms times 1.5 meters per second squared plus, and we're told the friction force is 100 newtons. Okay. And so we know what this is going to equal. This is 300 newtons plus 100 newtons. And so, of course, we get 400 newtons in total. Now, this should make perfect sense, right? Obviously, in order to maintain the same acceleration as before, the force of the wind must increase in the same amount as the new frictional force, right? So if there was no frictional force before, but now there is, the wind force has to increase that exact amount in order to maintain the same acceleration. Okay, so nice little problem, kind of gets us started with thinking about things that are accelerating, things that are not in equilibrium. Okay, very good. Next example. Let's do one that's a little trickier. It's got a little bit trickier kind of setup. So a loaded sled has a weight of 225 newtons. Okay. It slides frictionlessly down a long snow-covered slope. It slides frictionlessly down a long snow-covered slope that has a constant angle of 22 degrees. What is the sled's acceleration? And how fast is it moving after 10 seconds? Okay, so kind of a simple question, right? So we've got some kind of a slope here, and we're told that it's a long slope, not how long, but presumably long enough that we don't have to think about it ever ending. And we've got a sled on here, right, that's weighed down, has a certain mass of, what did this say, 225 newtons is the weight of this thing. Okay, and it's just sliding down this slope, no other forces involved there. It's a frictionless slope, so nothing is opposing, it's sliding. Okay, so this is the basic setup. Let's take a look at a free body diagram, and I think you can imagine what's going to make this problem more involved are the angles, right? The fact that we have an angle to deal with. So let's draw the free body diagram as best we can to start with. So the sled is here, and pulling straight down is the force of gravity, the sled's weight. Okay, and then perpendicular to the slope is the normal force. Okay, these arrows are not drawn to scale, so don't worry about that. I'm just getting the directions sorted out. Now, the sled is going to be pulled down the slope in the direction of, kind of downhill, right? So kind of in this direction. And so what we're going to basically end up doing is creating a triangle off of the weight here, right? So this you can think of as here 22 degrees, and then you're going to have the force offsetting the normal force, kind of like this. So let's coordinatize this so that this is the y-axis and then this is the x-axis. Okay. All right, and so what we need to know is we need to figure out what this guy is here, and we really need to know what this one is here as well. That's going to be kind of the thing that offsets the normal force. All right. Okay, so let's think of the triangle that's involved here. So consider the triangle. What's it going to look like? Well, I'm just going to draw it like this. We've got a 22-degree angle. We know that this is 225 newtons. Right? That's this piece here. The right angle is here. Okay, and so we'll put this as the, let's say this is x, and this is y. Okay. And we can say that x is equal to 225 newtons times sine of 22 degrees, and y is equal to 225 newtons times the cosine of 22 degrees. Right, just kind of doing the trig here quick. And so then, I guess what are these things? X would be equal to, I guess if you calculate this, right, you get about 84 newtons or so. And then if you calculate the y component of the weight, you would get about 209 newtons. Right, so most of the force of gravity is holding the sled on the slope, and the other part is dragging it down the hill. Okay, I think I labeled these wrong. Maybe that's x and y. Yeah. Okay, so then let's take this information and put it onto the free body diagram. So let's kind of revisit that with the new information. All right, so now we have the sled. We've got the weight of the sled, 225 newtons. We've got the normal force of 209 newtons. Make this a negative here because it's pointing down. And then you've got this thing over here offsetting that at negative 209 newtons. And then you've got the force that's pulling the sled downhill, right? And that's the 84 newtons. Okay. And so this is the y direction, this is the x direction. So obviously the y direction is in equilibrium. What we really care about is the x direction, right? So the sum of the forces in the x direction should be equal to the mass of the object times the acceleration in the x direction. Okay. And so that means we're talking about 84 newtons equals the mass times the magnitude of the acceleration. Well, however you want to notate it. You can write it like this, or you could write acceleration in the x direction. Right, we're not actually told explicitly what the mass of the sled is, but we know that the force, the weight of the sled is 225 newtons, and so we know that W is equal to mg, right? So if we're given W, we can figure out, and we know what g is, we can figure out what m is. M is equal to W over g, right? So the mass here is really W over g, and then times the acceleration, right? And so we have, what do we have? 225 newtons divided by 9.8 meters per second squared times the acceleration in the x direction, right? Okay, and so we can easily solve for the acceleration here. So a sub x will be equal to 84 newtons, and then we need to divide by this. We'll flip it over and multiply. 9.8 meters per second squared over 225 newtons equals, and you do that calculation, you'll see that this is about 3.66 meters per second squared. So the sled is accelerating at a constant rate of 3.66 meters per second squared. Perfect. Okay, so that's kind of that's the first part of the problem. The second part is very, very quick. We just want to know how fast is this thing going after 10 seconds. Well, we could say V final is equal to V initial plus AT. All right, so it's initially at 0 meters per second. It's accelerating at 3.66 meters per second squared times 10 seconds. And so 36.6 meters per second. So after 10 seconds, this thing is going pretty fast, pretty darn fast. Okay. Very good. So the tricky part here is just being able to reason about this free body diagram and figuring out what the triangle of that you need to sort out looks like, and then figuring out what those forces are. Okay. All right. Let's do one last problem in this section. Another one. This one I think is interesting because it brings it's a little bit subtle, right? And the first time you see this, you might kind of question how to treat this. So, a 1 kilogram block. Oh my goodness. My handwriting is so bad, and sometimes it's just a 1 kilogram block is pushed along a surface with a constant 9 Newton force. Okay, so you've got some block, you're pushing it across a surface. So it's 1 kilogram, 9 Newton push, okay, along a surface. Okay, so pretty straightforward so far. As the block moves, it pushes against a second block. It pushes against the second block with a mass of 1/2 kilogram. A mass of 0.5 kilograms. Okay, assume no friction. Assume no friction. Okay, so you've got this 1 kilogram block that you're pushing on. Constant force 9 newtons. It's pushing on this second block that weighs half as much, or has half the mass, weighs half as much. What's the question? The question is, what is the acceleration of the system? What's the acceleration of the system? And what is the force exerted by the larger block on the smaller block? Okay, so two questions here. What's the acceleration of the system? So you think of this thing as one unity. Obviously, it's going to accelerate together. What's that acceleration look like? And then secondarily, you're pushing on the big block's pushing on the little block. What is that push? How much is the big block pushing on the little block? Okay, so kind of a slightly different kind of question, a little bit subtle. Let's set up two free body diagrams. Let's think of them as separate bodies to begin with so we can reason about this. So we've got mass 1, okay, and it's going to have the weight, so W equals mg. There's going to be a normal force associated with that. And then the 9 Newton push will denote as F sub P, and that's 9 newtons given. All right, and then the other force that's being exerted on this thing is the force of the small block, right? So I'm going to call that force of 2 on 1. So this is mass 1, and then the little one will be mass 2, and it's pushing back, right? Because they're in contact, right? So the big block pushes on the little block pushes on the big block. There's action-reaction there, right? Okay, so this is the first mass. And what's the second mass look like? M2. Well, it's going to have its own weight. Okay, I'm just going to put mg, but technically that's m2g. I'll put m2. Make that m1. Okay, and then there's a normal force there as well, right? We're not so interested in these y forces. We're really more interested in the x direction here. And then the only force operating on this guy, it's frictionless surface, right? The only force acting on this guy is, what is it? Well, it's this force, it's the action-reaction pair that goes with this guy. So it's the force that 1 exerts on 2. So you got the force that 1 exerts on 2 and the force that 2 exerts on 1, right? Those are action-reaction pair, right? Okay, so we're only really interested in the horizontal forces because we're interested in the acceleration. It's obviously accelerating in the x direction, right? So we'll coordinatize this in the x direction. Okay, so let's think about the two free body diagrams as let's separately kind of write out Newton's second law for these guys. So we've got block 1, we'll say, and block 2. Now, what do we have here? So the sum in the sum of the forces in the x direction for block 1. Well, you got the force of the push, right, minus the force of 2 on 1. Okay, and that's going to be equal to m1 times the acceleration in the x direction. Okay, that's everything for this guy. Now what about block number 2? Well, block number 2 is again, the sum of the forces in the x direction are, well, there's just F12, right? There's the force that block 1 exerts on block 2. That's got to be equal to m2 times a sub x. Okay. Now, we can substitute some more things in here. We could say that this is 9 newtons minus F21 equals what? 1 kilogram times a sub x. And here we can add in the mass here. So this is F12 equals 0.5 kilograms times a sub x. Okay, we have 2 equation, 3 unknowns, right? So this is not solvable yet. What we'd like to be able to say, we'd like to get to 2 equations, 2 unknowns, right? Then we could deal with this. What can we say about these two? Right, so notice F12 and F21 are an action-reaction pair. Right, so what that means is that the magnitude of these two forces is the same. Right, that's key to understanding this problem. Right, and so what that basically means is that we can replace one with the other, right? However, whatever's convenient, we can plug in these they have the same magnitude. We're only talking about the x direction, all the forces in the x direction. So we can just swap them, can't we? Right, so instead of writing F21 here, right, we could write F12. So let's do that. So let's make our system look like this. The first equation is 9 newtons minus F12 equals 1 kilogram times a sub x. The second equation is F12 equals 0.5 kilograms times a sub x. Is this a system we can solve? Most assuredly, right? 2 equations, 2 unknowns. We can easily solve this. In particular, let's take this guy here and plug it in. Let's take this here and plug it in up there. Okay, so let me switch paint. Well, I'll write it here first. So 9 newtons minus, plugging this in, 0.5 kilograms times a sub x equals 1 kilogram times a sub x. Okay. And then we can solve this. And so what do we have? We've got 9 newtons equals, and we can bring them both to the same side, and we get 1.5 kilograms times a sub x. Right, and so The acceleration in the x direction must be equal to 9 newtons divided by the mass of the whole system, 1.5 kilograms. And you get 6 meters per second squared. Okay, so that's the acceleration of the whole system. Makes sense, right? The whole mass is 1.5. It's accelerating as a single item, as a single object. So that's what the acceleration must be. Now, to identify the force that block 1 exerts on block 2, we can just go back to that previous equation. Previously, we have this equation, F12 equals 0.5 kilograms times a sub x. Right? All we got to do, if we want to know the force that block 1 exerts on block 2, remember, block 1 is this guy, block 2 is the smaller one. There's a force being pushed, and the second, so you're pushing on 1, and 1 is pushing on 2. How much is 1 pushing on 2? Well, to figure that out, you just have to plug in this acceleration here. So 0.5 kilograms times 6 meters per second squared. And you multiply that together, and you'll see that that's 3 newtons. Okay, so the force that the big block is exerting on the little block is 3 newtons. Right, so the force being input into the system is 9 newtons, right? So I'm pushing on block 1 with 9 newtons. Block 1 is pushing on block 2 with 3 newtons. Right, so the force being input into the system is 9 newtons, but only about 1/3 of that is being transmitted to the smaller block in order to keep it accelerating alongside the first block. An interesting relationship there. I think before running through the calculations, you might just say, oh, it's 9 newtons. It's got to be 9 newtons, right? It's not. It's significantly less because the mass of the second block is significantly smaller. Okay. All right. Very good. That'll do it for this section. Again, we're just exploring different problem types that can come up when we try to apply Newton's second law specifically to systems that are accelerating, so systems that are not in equilibrium. Okay. In the next section, we'll take a look at some problem types involving friction, more complex situations involving frictional forces. All right. Until then, take care.